learning algorithms somehow embody some kind of priors or assumptions about the world. Because there's this thing in machine learning called the no free lunch theorem that says that there's no universal machine learning, and that you can't really have completely tabula rasa learning that can be successful. So you need some priors, some assumptions about the world, and they have to be powerful enough to deal with the curse of dimensionality. In other words, the fact that there's an exponentially large number of possible configurations of the variables that we're observing. So what is the assumption that's hidden inside deep neural nets? Of various kinds, by the way. And essentially it's compositionality, something, of course, that computer scientists have been dealing with for ever. And maybe it's not obvious to you, how does compositionality enter neural nets? Well, I'm going to try to explain that a bit. But basically it comes in two places. It comes in having what we call distributed representation. So let's say an image is going to be represented by a bunch of attributes that are going to be learned. And we're going to call this a representation of the data. And these attributes are not going to be mutually exclusive. So now the number of configurations of these attributes is going to grow exponentially with the number of these attributes. So we have a kind of compositionality of expressing things. But this is a kind of parallel composition. We can have this attribute take this value, then in parallel this other one takes this value, and this other one takes this value. There's another form of compositionality which is really important and gives the name to deep learning, which is that we have these multiple levels of layers of neural nets, so the deep architecture. And the compositionality here comes because what particular unit at a particular level computes is the composition of functions already computed by units at the previous layer. So any computer program, as you know, is a composition of function. Each time we modify the state of the computer by applying some computation, we are composing previous computations with a new computation. So composition is all over the place, but it wasn't something that people in machine learning have explored sufficiently. And I think there's still a lot to do. It turns out that these two forms of compositionality, we can prove things about them, so these exponential advantages actually can be mathematically formalized. One quick word to see why we get an exponential advantage from having a distributed representation. So if you look at many classical statistical or machine learning algorithms that I would say are non-distributed in terms of representation, what do? They take the input space and they break it into regions. And they're going to learn about where these regions are and what the answer should be for each of these regions, using data, of course. So, for example, clustering, you would have like one region per cluster. N-grams, you would have one region per configuration of the last k symbols. Nearest neighbors, well, each region would be one of the training examples. Kernel machines with RDF kernels, things like that. A lot of non-parametric density estimation, prediction, decision trees. So decision trees would break, of course, the input space using the structure of the tree, and typically access a line breaks. So what's common to all of these methods is the linear relationship that exists between the number of regions that the system is creating to define the input space, and the number of examples or parameters that you need to learn those regions. And you'd think that's the only way, right? If I'm going to be able to distinguish between 100 different regions in my input space, I need 100 examples. How could I possibly have less? Well, with distributed representations, you can potentially have exponentially less. So how's that possible? Well, consider this very simple neural net here with 3 hidden units and 2 inputs. And to make things really, really simple, let's make these hidden units binary. So they're just binary linear classifiers, meaning they say 1 on one side of a hyperplane and 0 on the other side. And so each of these classifiers defines two regions with two half-planes. But now we have all of these units independently deciding, to be 1 or 0. So the number of intersections of these half-planes, corresponding to one configuration of the hidden units, is now exponentially large in terms of the number of parameters. Right? So if you have 3 units, you can have up to 8 intersections, 8 configurations of those bits. The actual calculation is a bit more complicated, but this is the gist of it. So now what it means is that we can represent with a small number of parameters a function that looks complicated. But of course, this is only going to work under some assumptions. I mean, there's no free lunch, as I said. This is going to work if the will satisfies some kind of requirement. So what kind of requirements are we talking about? Let me use this example. Something that's funny. So think about a system that sees an image as input and discovers as hidden units at some level attributes that characterize the image. And I'm going to give names to these attributes, although this is not going to be something that we hard code, it's going to be something that the machine discovers. So let's imagine that one of the units is going to be turned on if the input image is of a person that wears glasses, and say another one is going to be turned on if the person is a female. Oh, that's a strange choice of words. And the third one is turning on if the person is a child, and so on and so on. So we're going to have hundreds of these attributes, say binary to keep things simple. Now what's particular here, and in my previous example, what would it take for this exponential gain I was thinking about? It's my title here, that each feature can be discovered without the need for seeing the exponentially large number of configurations of the other features. So to learn about whether a person wears glasses or not, you don't need to see images with all the possible configurations of the other attributes. Male, female, child, not child, tall, not tall, dark hair, whatever. So, wearing glasses is something you can recognize with a classifier that maybe needs order of k parameters, order of k examples to figure out what it is that characterizes having glasses or not. You don't need an exponentially large number of parameters for that thing. But of course, this is true of all the other attributes. And so the total number of parameters we need is going to grow more or less linearly with the number of these attributes, and not exponentially. Whereas the number of configurations of these attributes could be exponentially large. What that means is that we can now generalize to configurations. Maybe I've never seen a female child wearing glasses, but I have seen glasses, I've seen females, I've seen children, so I can generalize. Right? This is how you get generalization in neural nets. This is the power of district representation. The cool thing is that these attributes that I was talking about, actually they are discovered by these deep convolutional nets. So there's a nice study from MIT where we try to figure out what each unit is doing, what it likes, and we see units that somehow discover concepts like tables, lighting, people, animals, seeing. And although this is not the task here, it's supposed to classify different scenes. So these nets actually discover these kinds of high-level semantic attributes, at least in the higher levels. All right, and we can do math about it, and I'm going to skip this. Okay, there's another nice theoretical progress that's been made in recent years. There was a sort of myth, false belief about neural nets, which had pushed a lot of people away from that field in the 90s, which was the idea that, the training objective is non-convex, which means there could be a large number of local minima. In fact, you can prove that there's an exponentially large number of local minima. And so training is probably hopeless. Well, actually not. Actually, yes, there are an exponential number of local minima, but they happen to be good local minima rather than bad local minima. And to keep the story short, I'm just going to give you a little geometric intuition. If you draw a 1D curve, sort of a smooth random 1D curve, you're going to see lots of ups and downs, and for each up and down, there's a minimum and a maximum. So you think, okay, in sort of random functions, there's going to be lots of minima, it's going to be a problem. Some of them, say half of them, are going to be bad, right? And you'd be right. And in 2D though, it might be a little bit better if if you're a skier, like I used to be before my knees told me not to. You know that typically you don't get stuck. You find an escape route. In 2D, it's much easier to escape than in 1D. Well, turns out that in the 1000D, it's a lot better. In fact, it's exponentially better. To see this, you can think about critical points of the objective function. So in other words, places where the derivative of the cost with respect to the parameters is 0. And now you can think of how to characterize those critical points, because these would be the places where you could have a local minimum, or a saddle point, meaning the objective, the cost goes up in some directions and down in other directions, like in the picture on the right. So now the question is, how many directions is it going to go curve up and how many is it going to curve down? Because to get a local minimum, you need to curve up in all directions. And if the kind of function is chosen in a kind of sufficiently random way, then the chances that they're all curving up, if you pick a random place, is going to be exponentially small. Except when you're near the bottom, because now you can't go down, so it has to curve up in all directions. And so the actual local minima are going to be near the bottom, near the global minimum in terms of cost. And we verified this experimentally. All right, so let me go back to my little history. So in 2006 to 2011, we make, say, progress in our ability to train on academic tasks, deep nets. And this translates immediately into results in the area of speech recognition, and there's a big drop in error rates thanks to these deep nets. And very quickly, in about 2 years, industry picks it up. And by 2012, if you had an Android phone, it actually had deep nets doing the speech recognition in case you were shut off from the server and also on the server. And now it's everywhere. All of the commercial speech recognition systems use deep learning. So that was the first wave. It kind of changed the field of speech recognition. The second wave was even more dramatic. So it started with this 2012 paper at NIPS showing that these deep convolutional nets could, by Jeff Hinton's group, could actually beat the hell out of classical computer vision in a large object recognition task with about 1 million examples and 1,000 object categories called ImageNet. And by 2015, so computers can now do this. You give them an image and they'll do a pretty good job of identifying common objects like people, chairs, and dogs, and all kinds of things like this. This is the kind of evolution of the accuracy on this benchmark. 2011 was prior to introducing deep nets, and you see that we've essentially reached human level accuracy, at least in numbers. I don't believe we're doing as well as humans in terms of computer vision. Yet, the reason we're matching human level accuracy is that 20% of the categories in this data set are different breeds of dogs. And so the computer becomes a really good expert at all kinds of breeds of dogs that you and I can't distinguish. But it still makes mistakes that humans don't do. So there's still some progress to make, but it's really amazing how close we are to human level performance here. Of course, many companies, this slide is now getting old, have jumped onto deep learning since then. And more recently, there's been kind of craze is there a microphone? Well, let's try to get sound working. Let's cross our fingers. should have sound. No sound? Oh, there's no wire for the sound. All right, I'll do without sound. So, no, it's okay. This one, that's too bad though. This one is okay without sound. So these are pictures from some of my former colleagues at AT&T Bell Labs, who started a company which was bought by NVIDIA, and they started using convolutional nets to train self-driving cars. And you see that early on, their neural net isn't very good. Oops. Let's try this. Well, sorry about that. Computers, they're not yet intelligent, huh? All right, finally, we have something kind of working. This is what happens when you don't have enough brain data.
Whoa! What? Wrong way!
After 3,000 miles of running. You shouldn't do that. So there are still many obstacles before we all get a self-driving car. For one thing, GPUs that are required right now are way too expensive and way too energy hungry, but there are also fundamental issues that I'll mention later. Another kind of related interesting direction that has moved quite a bit in the last few years is everything that has to do with language and also combining images and language. So this is an example of work we did a couple of years ago where the computer is asked to produce a sentence in English which is a description of the image. So it looks at the image on the left and it says a woman is throwing a frisbee in a park. And it actually tells you for each word that is generating one after the other which part of the image it's looking at as it's choosing which word to produce. So when it's saying frisbee, it's actually looking at the frisbee. And in the second image, it sees this and it says the dog is standing on the hardwood floor. And when it says dog, it's actually looking at the face of the dog and so on. Let me show you another video, this time coming from my colleagues at Facebook, who have been doing something similar to this, but adding the element of question answering.
Is there a baby?
Yes.
So the answer comes from the computer.
What is the man doing?
Typing.
And it's going to give you different scores.
Is the baby sitting on his lap?
Different answers that it generates.
Yes.
Are they smiling?
Yes.
Is there a baby in the photo?
Yes.
Where is the baby standing?
Bathroom.
What is the baby doing?
Brushing teeth.
What game is being played?
Soccer.
Is someone kicking the ball?
Yes.
What color is the ball?
Yellow.
What game is the dog playing?
Frisbee.
What color is the dog?
Black.
Is the dog wearing...
One thing I want to mention is that...
Is there a baby?
Oops, that's kind of
Yes.
not what I wanted.
What is the man doing?
Typing.
Is the baby sitting on his lap?
Sorry.
Yes.
Are they smiling?
Okay. One thing I want to mention is that, that's better. Answering a question is very close to actually generating a sentence. So the way we generate a sentence is we generate one word after the other, given the previous word. So you can think of a question-answer pair as a long sentence which has a special form, where the last word or the last few words are the answer, and the first part is the question. It's essentially the same techniques that are used for generating sentences as for answering questions. Of course, what's going on under the hood is another story, but also the thing I want to mention is don't get too excited. This is a demo, and we're still far from AI. So one thing for sure is that neural nets are moving beyond their classical realm of pattern recognition. And this brings us into areas that are more, that have been investigated more in classical AI, precisely things like logic and reasoning and knowledge representation. These are the kinds of questions that people are thinking about these days with neural nets. And of course, there's a really hot topic these days, which also connects to classical AI, which is reinforcement learning, which brings in question of planning. And you've seen, I've mentioned the Go game playing, but there's also some really exciting work going on these days, in particular from Berkeley, Peter Abeel, on robotic control using machine learning. I think the whole field of robotics is going to be turned upside down in the coming years using deep learning. So to come back to reasoning, so what is reasoning? And I'm going to try to explain what reasoning is in a way that makes it sort of closer to how we think with neural nets. So reasoning, I think, is essentially sequentially combining pieces of information in order to come up with an answer. Let's see an example here. So the computer reads this little paragraph. Sam walks into the kitchen. Sam picks up an apple. Sam walks into the bedroom. Sam drops the apple. And then the computer gets the question, where is the apple? Right. You see that there's a sequence of pieces of information, each sentence, which actually, more or less corresponds to a triplet here of entities and relations. But if you were to directly simply look for the word apple, it's not going to give you the answer right away. I mean, it talks about Sam, but in order to find the answer, you actually have to look into the set of facts here and combine two of them. In particular, the third one has Sam walks into the bedroom, and combining that with the fact that Sam is the one who drops the apple in the fourth one, we can come up with the answer bedroom, right? So it's a very, very simple example. And so what has been done in the last couple of years is design what's called memory extended neural nets, which can sequentially combine pieces of information. And the way that they combine pieces of information is that they use what we called an attention mechanism, which I'm going to come back to in a couple of minutes. So before I tell you about attention, I'm going to tell you about machine translation, because we came up on the power of using attention by trying to do machine translation with neural nets. So initially, the way we tried to do machine translation with neural nets was fairly naive, maybe. We just use a recurrent net that reads a sequence of words and then produces in its state, a fixed size vector, which summarizes the whole sequence. Say we read a sentence in French. And then we have another recurrent net which generates the translated sentence, say, in English, just like the one I showed you that generates a caption for an image. In fact, the code we used for this caption generation project was exactly the same code we used for machine translation. So instead of going from image to sentence, you go from sentence to sentence. And in between, you have a representation of the input part. Here would be an image, or it could be a sentence in some language. The problem with this approach is that it works for short sentences, say 5, 10 words. When you go beyond 20 words, it starts having trouble. And to see, why there's no hope for this to generalize to long sentences. Think about trying to use this strategy to translate a book. So you would read the French book. Let's say you can understand French. You would read the French book. You would have in your mind a whole description of the content of the book, and then you would start writing the English book. Is that a reasonable strategy? No. How do we do it? Well, as a computer scientist, I would say we have 2 pointers, and we have a pointer in the French book and a pointer in the English book, and we keep moving both of them to sort of get the information that we need in the French book to produce the next bit in the English book. So that carrying of pointers is essentially what attention is about. So here's roughly what we did. We have some, neural net machinery, what we call a bidirectional recurrent net, which reads the French sentence and produces a sequence of feature vectors corresponding to each word in the French sentence. So now, at each position, we have a semantic representation that tells us about the word that's there, as well as the content, the context, and what it means, and it learns something. Somehow we're going to be using this to create our translation in English. So now we have another recurrent net on the top, which is going to produce one word at a time in English, and it's going to do it in the usual way for recurrent nets, meaning that it produces the next word given the state of the recurrent net, which summarizes everything that has been generated up to now. But it can also use the information in the source. And now, instead of looking at some aggregate of what was in the French sentence, we're going to use an attention mechanism to help the decision about what the next state or the next word in English should be by paying more attention in one or a few places in the input sentence. So the way we do this is we have a little neural net, the attention MLP, the red box here, which takes 2 inputs. One is the current state on the output side, which says, just before we're going to produce the next state or the next word, where we stand, what we have already generated in English. And on the input side, it's going to take the feature vector corresponding to one of the positions. And it's going to output a scalar, a score, that tells us, oh, this is a good place in the input for deciding what the next word in the output should be. In other words, this is a word in French, in the French sentence, which is very relevant to deciding what the next word in English should be. And then we are going to compute this attention score for every possible position, right? The attention is essentially something that says at each position we're going to provide more or less attention. So we have to compute how much attention we're going to give to every position. That's the attention score. So we're going to compute that for every position. And then we're going to take a weighted combination of the features at each of the positions weighted by these attention scores. And they sum to 1 by construction. And we're going to feed that weighted sum, which is an aggregate now, but it's an aggregate of just a few things that are relevant to decide what the next output state or output symbol should be. So that's the gist of how we use attention. And it's been incredibly successful. And just after we put out that paper, this idea of soft attention has been used to produce these question answering systems that I was mentioning before, where the same kind of attention mechanism now is used to look back in the input sequence at one or few sentences at a time to decide what to do next. And the system can now, it's not like a translation where, we produce one answer at a time. Here there's going to be several steps of reasoning. Like, so we're going to be putting our attention, presumably what's going to happen is, because the question has the word apple, it's going to focus its attention on the two sentences that have apple. And then, it figures out that, well, Sam seems to be an important thing. And because it's learned about reasoning and logic, it knows that the latest sentence is probably more important. And so it's going to look at the third sentence, which has Sam, and also has bedroom. So that's how it's going to extract the answer bedroom. But you see that in this process, it has to pay attention to specific sentences one at a time. How much time do I have? Oh, I thought you were showing me some time. Okay. All right, sorry. Okay, so it took us about a year, and we managed to bring our machine translation system to state of the art and beat a few of the, on a couple of language pairs to beat the state of the art in 2015 at the International Yearly Competition for Machine Translation. And over the last 2 years, there's been a lot of progress in the architecture of these neural nets. So it started with the soft attention, then ways to train faster.